Okay. Thank you for joining me. This is our prepping to get to the finals now. We're going to go ahead and go through some administration, talk about different things we're going to need for the final, and then if we have time, I'll do some highlights of previous chapters. So due this week is chapters 14 and 15 videos are up. You should be watching those already. Those are great. Chapter 16, I was trying to have up today. I've had intermittent internet because of the storm, but it seems to be working right now, so I'm hoping to have all 3 of those videos up. This is mostly going to be kind of a really lightly touching polymer chemistry, and it's a specialty of mine, so what I'll do is I'll kind of hit what I think are some highlights you should know. For example, that in polymer chemistry, it's all about very big molecules. I mean, you know, millions and millions of molecular weight. And so that's what we're going to focus on in that. So chapter 14, 15, and 16 videos will all be up this week. And those are our last chapters. Are going to be completed chapters 1 through 16, and we'll be ready to move into the final from there. Okay. Chapter 14 and 15 homework are due on Friday because I didn't want to have all that due all at the same time. Chapter 16 homework isn't due till Monday. If people have to work over the weekend, go ahead and email me. I might extend that till Tuesday. I can't move it past Tuesday because that's when reading day starts. So if you want me to move it to Tuesday, go ahead and chime in and I'll go ahead and move it to Tuesday. And it says here there's a quiz on Friday. Actually, I believe we've already done our quizzes. We have all of our quizzes done. So I think that was also a typo, is the fact that we don't have a quiz. Or do we? Let's see. We do have a quiz. Is that in this class? Let me double check this real quick. I thought, no, this is the only class we have a quiz in. Yes, we do have a quiz. We'll have a quiz on Friday. It'll be predominantly over chapters 14 and 15, okay? As I have a question here in the chat about will we be getting extra credit opportunities? Because this is such an unusual semester, I'm gonna have to say no with that. The overall class average is doing really well. Let's go ahead and finish up strong, and we'll balance out, you know, the changing in class and stuff. But I think overall we're going to finish this really strong. So, but go ahead and email me if you have concerns about your final grade. Let's see. So chapters 14 and 15, quiz on Friday, and homework is due on Friday. Chapter 16 videos released today. Homework on that isn't due till next Tuesday. In fact, I'm going to go change it right now because I think it should be due on Tuesday. Let's see, chapter 16, due May 5th. There we go. I just changed it. There we go. So it's due May 5th. Okay. Let's see, what else do we have here? Okay, the next most important thing that we need to talk about this week is our final. Because of the different professors, I don't want to overlap other people's finals, so I'm giving it at the day and time it was originally scheduled. We are scheduled for our final on May 8th at 11 a.m. to 1:30 p.m. Please have some time set aside for that. Get your work schedule or childcare situation situated so that you can take your final during that period of time. It will be on sampling. It'll be a multiple choice question, A through, you know, A, B, C, D. There will be no drawing. It'll be all multiple choice and all on sampling. So go ahead and block out that period of time. Have your notes and your book ready, and go ahead and just take the test at that time. Okay, so that being said, that's what's going to be done this week. That's what needs to, you need to block out your time for the final on Friday, May 8th. right there. Again, it's all multiple choice and it's all on sapling. Okay, so the next thing I want to talk about is how I think you should prepare for the final. It is open book, open notes, but you only have 2.5 hours. You don't have time to just not study and just show up with a book. Okay, so that being said, I think I have a couple ideas that would help you with that. And the way I think you would really benefit you to study is to prepare ahead of time some review sheets. So the review sheets I think you should look at are, number one, go ahead and get a sheet with nomenclature. Okay, now the best way to start this probably is looking at carboxylic acids, because carboxylic acids is where we talked about the priority work. Carboxylic acids are the highest priority. So if you have one, that's what it's going to be named for. And then work all the way back to your alkyl halides. Remember that ethers and alkyl halides are substituents. When we named amines, those are less priority than aldehydes and ketones, which are less priority than the carboxylic acids. I have a question here in the chat about will it be timed, or do we have those times to finish it? It will open at 11 a.m. and it will close at 1:30 p.m. You only have that time to be able to do it. Okay. You should be able to go back and review questions before. No, I don't know that question. I have another question here about will you be able to go back and review questions before submitting? I'm not sure. I'm actually taking a workshop tomorrow on that, so I can answer that question if you email it to me. I'm taking a workshop on, can I have you just review it, or do you only get the one shot to answer the question? Okay. You will have the entire time available to you to take the test. Going back to the previous question, you'll have the entire 11 a.m. to 1:30 p.m. to take the test, but at 1:30 it will shut off. Okay, so you only have that time period to take the test. Students with accommodations will have extended time, and you'll have a different login for that. Yes. Okay, yeah, I've learned how to do that part at least, but I'm not sure about the going back and reviewing questions. I think that's a good idea if I can get that to happen, but I take my my training session tomorrow afternoon, so I'll know more then. Okay, all right. I'll keep watching the chat box, but let me go back to the review sheets that I think you should build yourself. Now, the value in building this yourself is, number one, it gives you a chance to review and organize the different information into different sheets, okay? So what I'm suggesting is you do, number one, your nomenclature sheet. You look at, and you have, you know, like, oh, carboxylic acids are most, and if I have these substituents on a carboxylic acid, this is what I use. For example, if you have an aldehyde and a carboxylic acid, you have to name the aldehyde as an oxo. It's no longer an aldehyde because the carboxylic acid takes precedent. So build yourself a nomenclature sheet with all the nomenclature rules starting from chapter 1 all the way through to the amines. Carboxylic acid derivatives, actually. That should take you across the entire spectrum of nomenclature. Now, we're going to start with the simple ones. You know, find the longest chain, name your rings first, then which functional groups are highest priority, doing your lowest numbers, putting things in alphabetical order, di, tri, tetra, E and Z, R and S. All of that should be on your nomenclature review sheet, okay? So, and it might not happen all at once, or it might be best to do it digitally, because it's like, okay, this row, oh, where did this row go? And you can rack and stack them and build your sheet. The value in you building your own sheet is you're reviewing it as you go. Now, after you've built a sheet, go ahead and maybe share it with somebody else and say, hey, do I have everything? And do it that. But you actually get so much more value out of it building it yourself. Like your nomenclature sheet should take you 30 minutes, maybe 45 at most. But it's reviewing every single rule and get them all in order so that you know exactly how to name everything. Okay. The second sheet I think you should build is a bonding sheet. Okay. So in the bonding sheet, we learned a lot of different things, like Number one, a sigma bond is 2 electrons. Okay, a sigma bond is an sp3 hybridized orbital. Okay, a pi bond is a sigma bond and a p bond, right? So the pi bond is the double bond, and it's one sp2 hybridized single bond and then one p overlap. And a triple bond, oh, that's an sp hybridized sigma bond and 2 p bonds. So build a bonding sheet. Look at hybridization and shapes. Remember that sp2 is a trigonal planar. The sp1 is linear, okay? So in that bonding, you also want to look at different types of bonding. You have van der Waals interactions, or just the induced dipole, induced dipole, dipole interactions, hydrogen bonding, and ionic interactions. Look at all those different types of bonding and kind of rank them by strength, okay? So that, I think, is also kind of a value because all chemistry is bonding, right? We're doing different types of bonds and different strengths of bonds. And within that bonding, you want to also look at electrophilic, you know, which is more electrophilic and less electrophilic, because that'll give you a polar bond versus a non-polar bond. And remember that polarity changes hydrogen bonding. Remember, because the thiol, because they're so close, that doesn't hydrogen bond. The amine has polarity and does hydrogen bond, but the alcohol has the biggest polarity and hydrogen bonds the strongest. So all of those kind of things would be what you would want on your bonding sheet, okay? So we have our nomenclature sheet and our bonding sheet, okay? The next thing I think you should do is make a sheet on properties, okay? So this is associated with the bonding sheet. Think about how the different properties change by the different types of bonding we have. So it's kind of like as we go from hydrocarbons through carboxylic acids, we see that the induced dipole have the lowest melting because they have the lowest interaction, right? But what also affects melting point and boiling point is molecular weight. As the molecular weight goes up, melting point and boiling point goes up if there's no other interaction. Dipole-dipole interactions, like in ketones, change the boiling point, and that affects it more than van der Waals, but less than hydrogen bonding. And then carboxylic acids, of course, have the highest melting and boiling because they do the most hydrogen bonding. So kind of have this properties as a correlation between the types of bonding, molecular weight, and the shape of the molecule. The more spherical a molecule is, the less interactions it has, therefore the lower boiling and melting point it has. The longer or more polar the system is, the more bonds and the higher it has. So that kind of building that property sheet will also help kind of solidify all the different properties we've been talking about and how they, oh, well, that's why ethers are lower boiling than alcohols, even though they're the same molecular weight. Or that's why alcohols have a higher boiling point than amines because of the hydrogen bonding. These kind of correlations, it's really good to have it all in one sheet. And so you can like look for those commonalities, and you know, it'll start to make a little more sense now that we're going to correlate the entire semester all into one place. Okay. Now, the last sheet you should do is what I call the reaction sheet. Okay. So we have several different reactions we do. For example, it would be something to look kind of like this. I'm not going to give this one to you because there's value in building your own. But the idea is you start on a transformation. Okay, if I want to turn an alcohol into an aldehyde, how can I do that? Okay, so the first column is what transformation I'm going to do. Second column is what reagents I would do to do it. And then the third one is what I would call complications. Like, for example, in this case, if I convert an aldehyde, an alcohol to an aldehyde, first of all, I want to use a specific reagent, in this case, PCC, or pyridinium chlorochromate. And it only works for, if I have an aldehyde, it'll turn a primary alcohol into an aldehyde, but it'll turn a secondary alcohol into a ketone. So those are kind of that would be the complications column there. And so we have turning alkenes into alcohols. We do that with water and acid. We have turning alkenes into halides by adding an acid halide across it. We have converting ketones into alcohols by using sodium borohydride. We have all these different reactions. So you want to take one functional group, convert it to the next functional group, the chemical, and then what specificity. For example, let's take a tertiary alcohol, okay? If we're going to convert that to an alkyl halide, we know we're going to go through a carbocation. That kind of thing would be in our special notes, okay? So, and in that special notes area there, you'll be things like, okay, tertiaries in a strong base, so I'm gonna convert an alkene, an alkyl halide to an alkene, and I have a strong base, so it has to go through an E2 mechanism. Those kind of things are just the correlations. So if you run through and take each reaction from our notes and turn it into just a little, few notes on a page, then that will kind of try to draw the entire semester all into, oh, okay, so we only did, 35 reactions or 45 reactions, and this is the specificity about this one, and this is the specificity about that one. I think that right there, it does a great job at summarizing what we've done. It does a great job of getting you to look at all the different things we've done. And on this sheet, on these sheets you have, also put like page numbers or chapters where they can be found, where you can find additional information. So you don't have to rewrite the whole book. What you're doing is you're creating a sheet that you've organized in the way you think, and then you also have like page numbers. Oh, amines are on this page, and carboxylic acids are on this page. So it gives you basically you're making your own table of contents that follows you the way you think, okay? So questions or comments about making those review sheets? Okay, we got about 16 participants here, but you can, let's see, no new stuff in the chat that I can see. Actually, can somebody post something in the chat? I want to see if I'm frozen or not. Okay, there we go. Thank you. All right, so this is what I think is a really good idea about getting us to get ready for that final. Remember what we did in the early half of the semester, kind of correlating that, oh, alcohols do this and this. I can, we made alcohols, but then we've converted them into other things. Like we can take an alcohol, convert it to an alkyl halide, and then we can take that alkyl halide, turn it into an alkene. So we can actually do a lot of chemistry that goes all the way around in a circle. We've learned a lot of reactions, but we need to remember that we have those and what the different conversions are. And we don't want to get overwhelmed like, oh, there's 75,000 reactions. Well, no, there's a few reactions we have. Those reactions we have are logical sense. We take them step by step. Oh, I can convert the alcohol to an acid halide or an alkyl halide. I can take that alkyl halide, do SN2 reactions on it, and generate this cyano group. I can take that cyano group, hydrolyze it, and turn it into a carboxylic acid. So we can do any of these reactions step by step, knowing which functional groups we want to go from one to the next, and then having those special little things like complications. For example, when we do certain reactions with Grignards, we are forming carbon-carbon bonds. If we're displacing an alkyl halide with a Grignard, we only need one equivalent. If we're reacting that Grignard with an ester, we need two equivalents. So those are the things we would want in our special notes or complications table. Okay. So that being said, I'm gonna go over this again on Friday for those of you who didn't do it, and I will maybe show a couple other examples of things I think you should make sure you include but I want you to start building these things as we go, okay? All right, that being said, does anybody have specific questions over 14 or 15? If, how many questions will be on the final? That's a good question. I'm targeting evenly, distributing over the entire semester, so that I'm not sure it's going to be around 50, but I'm not sure exactly. I want to make sure I have an even blend over the whole semester. So, but my target is somewhere around 50. Okay. Okay. So we also have, for those of you who are in the lab, if you turned in your carbohydrates lab, that is the last thing we're doing for the semester. There will be no lab final. There will be no lab checkout. I'm meeting with your lab instructors this week, and hopefully they should all be done grading, and we can go ahead and look for your final grade in the lab here pretty quick. But the lab, if you've turned in your carbohydrates lab, is done. If you haven't, turn it in very quickly. So, because it was due on Monday. Okay. I think I have, at least one of the lab instructors has completed all of the lab grading. I think the other one's almost done. So we're going to do, so the lab grade should hopefully be assigned by Friday, if they all get their grading done. Okay. Let's see. All right, so if nobody has questions about 14 or 15, so 14 was carboxylic acid derivatives and interconversions, and 15 was all about enolates and the idea that it's a carbonyl reaction. Thank you. All right, it looks like I'm back. Can everybody hear me? Yes, I was muted, I'm back. Yeah. Sorry, had a glitch on the internet there. It's been going in and out, so we'll see that. Okay, so I believe you might have heard up to the part where chapter 14 and 15, where we were looking at enolates and carboxylic acid derivatives. The key about enolates is we're using that carbonyl to activate that one carbon over. And the key with carboxylic acid derivatives is you always go from a less stable derivative to a more stable derivative, and then you have to hydrolyze and go all the way back to carboxylic acid to get them back up. Okay, if anybody has any questions about those, go ahead and put them in the chat. If not, I'm going to go ahead and hit the high points of chapter 16. Okay. Grab a sip of coffee here. Okay, let's see if my iPad will let me hit the highlights of chapter 16 here. Come on. We're sharing, yay. All right. So let me go ahead and put the chat up here. So go ahead, and I have the chat up here. So if you chat, I'll look away here and see if there's anything in the chat. All right, so our last chapter. Okay, the cool thing, well, I'm a polymer chemist, so this is a really good topic for me. But the key here about polymer chemistry is that we're looking at very big molecules, okay? And there's a bunch of different ways to make them, and there's a bunch of different kinds. And so when you think about polymer chemistry, think about plastics, okay? So a polymer is just a whole bunch of the same monomer unit linked together, okay? This is different than a protein because proteins tend to be different types of amino acids hooked together. Carbohydrates tend to be sugars or saccharides added together. In polymer chemistry, we're typically looking at non-natural polymers, non-natural molecules, okay? Most of the time in polymer chemistry, we're looking at petrochemical derivatives or natural chemical derivatives we get from other places other than starches and carbohydrates and proteins and fats, okay? So a monomer is just the smallest unit you can break it down into. Plastic is a generalized term that means a big molecule that can be molded. Now, there's two different ways to do this. There's one where you can take it and you can mold it again and again and again and again, like polyethylene, or which is plastic bags, or stuff like polystyrene or polycarbonate, which are glasses. Your glasses are made out of polycarbonate. Those can be molded by heating and pressing into a mold, and then they can be remolded. Now, this is opposite of something like an epoxy. And an epoxy, like when you squish out and you can bake it, and it'll do what we call a thermoset, meaning it's molded once, and once it hardens, you can never undo it. Okay, so thermoplastics are things that can be molded and remolded. Thermosets are you set it and it's done. Okay, so we'll have all these different types that we'll see in there. And so it really has a broad range of different things we can do, and they're made a bunch of different ways. Okay. So in general, okay, we're going to share again. Technology, yay. What are we looking at here? Okay, let's see if that's why. My iPad decided to switch Wi-Fi channels. Come on, share. There we go. Okay, so basically a polymer is just a whole bunch of units added together, and they can be added in a bunch of different ways. And because we don't know exactly how many, we call it the average number, or this little n that we see here, is because it's just some kind of number right here. This little n means we have some number greater than 1 in there. And it can be, this n can be hundreds to thousands to millions. It really doesn't have a specificity on that. Okay. All right. So when we name polymers, we just basically add the word poly in front of the name of the chemical it was made out of. So that's nice and easy. So for example, we have this molecule here, and we learned in the benzene chapter that this vinyl benzene is called styrene, and therefore we just say polystyrene. This right here is a chlorine next to a vinyl group, so we call that vinyl chloride, so we call it polyvinyl chloride. Okay, it's nice and simple. There are IUPAC names, but almost nobody ever uses them, so we're not going to worry about that. So the cool thing about polymers is, you know, small molecules, they'll have 1 or 2 conformations, and then that's about it. Well, in polymers, you can have just straight chains. You can have chains that have branches off them. You can have regular chains all the way down to turn them into combs. And all these different shapes have different properties. So that you can spend your entire career just studying star polymers and saying, oh, these star polymers do this one thing. Or dendritic polymers. I'm going to do this. I'm going to release drugs using dendritic polymers, and they'll slowly release a material. So there's a lot of variety in here. Okay. The cool thing about polymers is that you can have either them crystallize within themselves, or you can have them be non-crystalline or amorphous. The interesting thing is that polymers, when they're crystalline, are opaque, and when they're amorphous, they're clear. So it's not crystal clear, it is crystal opaque in polymers, and amorphous clear. So what we call those is, so basically amorphous have no crystals in them, and crystalline do have polymers in them. Okay. Now, this difference between having a crystalline section and a non-crystalline section not only changes the clarity of the polymer, but it also changes the strength of the polymer. And we'll learn about that in the next one over. Okay, so and a good example of this is PET, your plastic bottles. That's polyethylene terephthalate. When it's dried, when it's cooled very quickly, it's nice and transparent, clear bottles. When you actually stretch it into fibers, so when you have polyester fibers, those are also PET, those are actually opaque, and they are opaque, and then you dye the outside of them, and that's what they get their colors from. But they are, those properties change. The plastic bottles are actually fairly flexible, but if you actually look at these fibers, they are very strong and very tough. All right, so I'm gonna, go ahead and put your questions into the chat there. I'm gonna go over the number 2 section here, which is 16.2, which is step growth. Okay, in polymers, we have 2 primary types. We call it step growth, where we're adding 1 unit at a time, and usually they have alternating functionality. So we add a carboxylic acid and amine, a carboxylic acid and amine, carboxylic acid and amine. And this is what we call step growth, okay? The other type is the next video over, which is chain growth, where we start with 1 monomer unit, and it keeps adding monomer units, but they all add in the same fashion, typically a radical formation, where we generate a radical each time we go. But in a step form, we usually alternating functional groups. Okay, that's the primary thing we have here. And this is used to make a whole bunch of different things. Polyamides are also called nylons. Polyester, that's PET, polyethylene terephthalate. Polycarbonates are used for eyeglasses, specifically resistant eyeglassware. Polyurethanes are usually very flexible and usually made into foams. And then epoxies are the kind of 2-part materials that solidify and make a nice hard material that never redissolves. Okay, so I'm going to hit the top ones here. Nylon is an alternating carboxylic acid amine, carboxylic acid amine, carboxylic acid amine. And so the simplest one we have here is what we call nylon 6,6. The reason it's 6,6 is because there are 6 carbons in the carboxylic acid, and there are 6 carbons in the amine. So it's 6 carbon carboxylic acid, 6 carbon amine, 6 carbon carbon, and they alternate back and forth, back and forth, back and forth, back and forth. And then it derives its power, its strength, and its the strength of its fibers, because when we pull it, as we're forming it, we have all the different groups here. These little groups here can hydrogen bond with themselves. Okay, so what we see that is here. Those little groups and the carbonyl of one chain hydrogen bonds with the hydrogen on the nitrogen on the other chain, and that's where it gets its strength. Hydrogen bonding is adding the strength to the polyamide or the nylon. Okay, we have another. Okay, so you can read about this or hear about this in the next video. But the next one I want to hit is this nylon 6. And in nylon 6, there it is, we actually have 6 carbons in between the amine and the carboxylic acid. But instead of actually starting with the linear molecule, we actually ring open it. So we have this ring-shaped amide, and we end up opening it as we make the system. So that's why there's only a single number there, because we have both the carboxylic acid and the amine in the same functional group, in the same monomer, but it's still alternating amine, carboxylic acid when it grows. Therefore, we call it a step growth polymer. Okay, so another amide that is really well known is called Kevlar. And in this case, instead of having those aliphatic chains, it has benzene rings in between the carboxylic acid and the amines. So we have an aromatic carboxylic acid and aromatic amine, and this makes it super, super rigid. And then it still hydrogen bonds like the nylon does. So now you have super rigid plus hydrogen bonding, which makes it super strong. So it is, the weight to strength ratio is higher than that of steel. because it is so strong in comparative to its weight. And it's most commonly used in bulletproof vests. Okay, that brings us to our next thing, a polyester. So it's just our ester functionality. Carboxylic acid, alcohol, condenses to form an ester, right? So in our step growth polymerizations, we have carboxylic acid adding to an alcohol, carboxylic acid, alcohol, etc. And PET, or polyethylene terephthalate, is the most common one. It's used in fabrics like Dacron or in plastic bottles, as well as the Mylar. Those Mylar balloons, that's actually polyethylene terephthalate with a thin layer of aluminum metal on it to stop oxygen or the helium from permeating. So that same polymer is used for those three different uses. So that's what makes polymer chemistry really, really interesting, because you can do so many things with it. So that's an ester. And these are typically made in a couple different ways, and I'll talk about that in the video. The next thing to talk about is polycarbonates. Now, Lexan is a polycarbonate. It's the most well-known one. It uses the compound bisphenol A, which might be an endocrine disruptor. There's been some data for and against it, but we'll see. Anyway, so bisphenol A could possibly be an endocrine disruptor, but it's made by taking the alcohol of benzene, or the phenol, and reacting it with a derivative of carboxylic acid, which is the phosgene. It's basically the diacid derivative of carbonic acid. And so when we polymerize this together, we make a very nice rigid material that makes a very clean, very tough plastics. But it's almost an ester, but it's technically a carbonate. And so we call it a polycarbonate. Okay, that brings us up to our polyurethanes. So when we make a polyurethane, we typically react an isocyanate, which is this derivative here. And if you'll look at it, we actually made these when we looked at that, one of the reactions we did with the imines in the Michael addition reaction. We actually made these as a derivative that decomposed during the reaction. We react those with alcohols to create this urethane, which is a carbonyl with an oxygen on one side and a nitrogen on the other. So we call those urethanes. And they typically can be used to make fibers, or most of the foams we look at, the rigid foams and the flexible foams, are polyurethane foams. And they do that because they can react with this isocyanate with a little bit of water, and it generates CO2 in the process, and it'll actually create a foam in the system. So polyurethanes are frequently used as foaming agents. All right, let's see how we're doing on time. Okay, we're doing okay. Text box I still have here. Nobody's yelling at me yet in the text box. Okay. And so the last of the step growth polymers I want to talk about is the epoxy resin. So in the epoxy resin, you think about the epoxy glue, you have two parts. One part's clear, one part kind of smells funny. Well, what we have happening there is epoxy resins typically are made where we have at least one, typically two or more of these ringed structures. Okay, this is a cyclic ether right here. And a lot of times we put bisphenol here. This is the same as in the polycarbonate. We put this bisphenol compound in the middle of it. And what that means is that this side reacts and then this side reacts. And so then this will actually produce an alcohol which can react here. So sometimes we get up to 4 reactions on these ends, which is why it never goes back into solution. It'll never be dissolved. It just creates so many cross-links that it'll react again and again and again. Now, most of the time when we have these these epoxies here, we react them with amines. That's the part that smells in that 2-part epoxy. So one's going to be kind of yellowy and kind of smell funny, and the other one's going to be thicker and more clear. So this component here is the thicker, more clear one here. And then this is the one that smells, right here. And when you react them together, it ring opens that chain and it extends and gets bigger and bigger. A lot of times you can have multiple functionalities on this amine and multiple functionalities on this epoxy. The more functionality, the more cross-links. The more cross-links, the harder the material is when it's done. Okay, any questions on step growth polymers? Okay, I'm gonna see if I can pull up my third one, which is chain growth. Now, chain growth polymers introduce a new functional group that we haven't done up to now, and it's called the radical or the free radical, okay? So in a chain growth polymerization, what we generally do is we produce a radical from something with a double bond in it, okay? So if we think about the simplest compound we have with a double bond, we have ethylene right here, okay? It's just 2 carbons and 4 hydrogens and a double bond. And we're taking that double bond and breaking it into 2 radicals and making 2 new sigma bonds, extending the chain. And so it's growing from that chain to the end using that same monomer unit. Okay, so let's look at that functional group again. The functional group we have is called the radical. Up to now, when we make a bond, we move 2 electrons to generate an anion and then the corresponding cation over here. And we use those 2 electrons to make our new sigma bond. In this polymerization, we actually break the bond such that we have 1 electron on each side. Because of that, we have an initiation step where we make the radical. We have the propagation step where those radicals keep reacting until they run out of things to react with. And then we have the termination step, which is when that radical is finally taken away and it no longer reacts, okay? So let's talk about those 3 steps right here. So the first thing we want to look at is we're introducing what we call the fishhook arrow. The fishhook arrow means we're moving a single electron. The regular arrows, we have the 2 barbs on it. We are moving 2 electrons. Here we're introducing the single barbed arrow or the fishhook arrow. What that means is that bond breaks, that sigma bond breaks, leaving 1 electron on one atom and 1 electron on the other atom. This single electron is our radical. This is our very reactive species that we have now. Most of the time we use an initiator, meaning we have something like an oxygen-oxygen bond that breaks apart very easily. And so we usually tend to use a peroxide or in this case, a peroxy acid that we break it apart and we generate that radical. So that's the first step in the reaction, is generating the radical or initiating the radical, okay? The next thing we do is we do what we call the propagation step. That means that radical that you generated from the initiator with either heat or light attacks a double bond, generating the initiated chain plus a new radical, okay? When a radical attacks a bond, it can only generate another radical unless a radical reacts with another radical to terminate the step. So anytime a radical reacts with a neutral species, it generates another radical, which then reacts and then generates another radical and reacts and generates another radical. So this is a very fast reaction because all we're doing is moving an electron. And we can generate as many radicals as we have initiators starting with. Okay, so let's talk about that propagation step. Okay, so we generated our initial radical here. When our radical reacts with a double bond, 1 of the electrons goes here to make our new sigma bond. The other electron from that pi bond stays here and is now reactive again. That one then can react with as many other molecules as there are double bonds. And every time it reacts, it generates another radical, okay? So it's just going and going and going and going, and there's nothing stopping it until we get to our termination step, okay? In our termination step, we have to have another radical react with a radical. So it either is reacting with another chain that's growing, or it has to react with that initiator that was created at the beginning. So that's the only way to stop a radical reaction, is to have a radical touch a radical, okay? Because remember, when a radical hits a double bond, it creates another radical. So we have to have this radical-radical reaction to terminate the reaction. That's the cool thing about the chain growth polymerization. We have those 3 steps. Initiation to form a radical, the radicals react until there are no more double bonds, and then those radicals react with each other to finish or terminate the polymerization. Okay? What's really cool about this is, because the radicals are formed in a specific way, you tend to get very regiospecific reactivity. Okay? So the radical, the more substituted a radical is, the more stable it is. Therefore, you're going to tend to form the same part of the molecule is going to react with the same part of the next molecule. And they are very regular pattern in which they react. Okay, so this is just how to do them. And this is a couple of catalysts. We're not going to worry about this, but what I want to do is do the last thing here is, okay, so our chain growth has to do with everything about creating a radical. Notice that these are all the different monomers we can make these radical polymers. Every single one of them has a double bond, okay? So we initiate a radical, that radical reacts with one of these double bonds, and then it just keeps going and going and going until it terminates. So it really doesn't matter what the double bond is. It can be anything, because we're not worried about whether it's forming an anion or a cation. We're not worried about if it's electron rich or electron poor. It doesn't matter, because the radicals are not charged. So if we look at our simplest one, ethylene here, it makes polyethylene. It's used for a lot of different things. We add just a CH3 group there. That's neither polar, that's neither electron withdrawing or donating. It polymerizes to make polypropylene. Add a chlorine. That makes vinyl chloride, or PVC, which we use for plumbing. Add 2 chlorines. It still reacts. This makes a really cool thing called saran wrap. It's a nice stretchy, partially chlorinated polymer. You add a withdrawing group like a cyano group, acrylonitrile. This is used in a lot of different things, including superglue. You add fluorines to both sides. That's really cool, because now you have tetrafluoroethylene, or Teflon, because it's all fluorine, nothing will bond to it. So it's really, really special that way. This is styrene. Having those benzene rings attached to it gives it a certain toughness that you wouldn't have. And also it allows it to be very soluble, so you can make it into foams like polystyrene foam cups. You can make it into polystyrene plastic clear cups. You can turn it into a bunch of other kind of impact resistant materials as well. And then let's say you have esters here. You can have these acrylate esters. So this ester functionality makes it easily suspendable in water, and therefore it's used in paints that you've suspended in water. That's what a latex paint is. It's a polymer that's not completely polymerized. It's suspended in a water emulsion. And then we can also do something like polymethamethacrylate. Polymethamethacrylate is also used as plexiglass. It's not quite as tough as polycarbonate, but it's nice, clear glass, transparent material. Okay, so those are the highlights of chain growth polymerization. And those will all be in the 3 videos that'll be posted hopefully by the end of the day if my internet behaves. Okay, does anybody have any more questions? If not, I'm going to go ahead and stop recording, and then we can just add questions either in the Zoom chat, or go ahead and unmute and talk to me also.